Hello friends, today we would look at how the atomic models evolved over time. So the story of atomic models, actually the most important model in that story, one of the most important model was the Thomson's 1904 model, which is the plum pudding model. So this would be our starting point. Then came the Rutherford experiments, and those were conducted from 1908 to 1910. The findings of the Rutherford experiment actually disproved the Thomson's model. So Thomson's model was gone after that, and we came up with a new model, which was the Rutherford's model. Rutherford's model, of course, like everything in physics, suffered from some drawbacks. So we had to improve it, and we improved it using the Bohr, Rutherford, or simply Bohr's model. So let's start with the very first model, which was the plum pudding model given by J.J. Thomson in 1904. See, even before the Thomson's model, people understood that there were some things called atoms. Atoms were composed of negatively and positively charged particles. So they understood this, okay. So the main thing they understood was there was something called electrons, and there was something called an atom, which is neutral. So because an atom consists of electrons which are negatively charged, and the atom itself is neutral, therefore there has to be something positively charged inside the atom. So this much they understood. Of course, the problem then was the technology. They were not able to actually see through the atom to find out what its exact structure was. And that's why they came up with these models which explained what they were seeing physically in the real world, which were able to explain their experiments. And that's why these are known as models. They are not the real structure. They were never sure that this was the real structure. They always came up with a model which would understand help them understand their experimental findings. And of course, when some new experiment was done, they found something new. The previous model was discarded. New model came along. Okay, so prevailing model, one of the most important models. There were other models also at that time, but the prevailing model was the Larmor's solar system model. Larmor's solar system model was most simple. What it said was, in the center there was positively charged, just like sun. Sun is there in the center of the solar system. So just like that, in the center there is a positively charged particle inside the atom, and around it revolve the electrons. The problem of this model was that, according to the classical mechanics, okay, the mechanics that we deal with in our daily life, according to that, what would happen if an electron were to revolve around the atom, around the positively charged nucleus? Okay, at that time they didn't call it nucleus, but if the electron were to revolve around the positively charged particle, whatever it was, it would slowly lose energy. Because it would slowly lose energy, it would slowly and gradually, it would become slower and slower. And as it becomes slower and slower, due to the positive negative attraction between the positively charged center and the negative charged electron, due to that attraction, it would collapse and it would fall inside the center of the atom. So that was the biggest problem with this Larmor's solar system model, that it was not able to explain the stability of an atom. And of course, if the atoms are not stable, we cannot really exist. So this was not a small drawback, it was a pretty large drawback. So to remove this problem, Thomson came up with this another model which did away with the rotating electrons completely. Okay, so if the electrons were rotating around a center particle, there would always be this problem. So Thomson came up with the plum pudding model, which did away with this rotation of electrons. It did away with it completely. According to this, in the structure of atom was very simple. There was the entire atom consists of positively charged. So the positive charge was distributed throughout the atom, and inside this were embedded this negatively charged electrons. So if you have eaten a chocolate chip cookie, okay, this is what it looks like. There are chocolate pieces embedded in the cookie. The cookie itself is entirely positively charged, that is the whole atom, and inside it are embedded these chocolate pieces which are like the electrons. So they called it plum pudding model. So plums were negatively charged plums, okay, and similar to our chocolate pieces in the cookie, and the entire atom was a pudding, which was of course the positively charged entire atom, of course. So this was the prevailing model. It gained a lot of support because it did away with the problem of the Larmor's model. And of course, we now know that this was also completely wrong. Atoms are not like chocolate chip cookies. Then came the famous experiment of Sir Rutherford. So Sir Rutherford, or Rutherford, what he did, see, he was primarily, you have to understand that he was primarily interested in the nucleus of an atom. That was his research focus. That is what he was working with. So he was not so much concerned about where electrons were or how they revolved and whatever. He was mostly concerned about the nucleus. What was it composed of? How did it behave? Okay, so to understand this nucleus of an atom, what it did was that he did an experiment. These are known as Rutherford Experiment. Of course, Rutherford was not alone in these experiments. There were two of his other friends. Hans Geiger, he was the first one. Okay, so he was there from the beginning, and later on some of the experiments were also conducted by Ernest Martin. So those were the two other people involved together with the Rutherford. Rutherford, of course, was the organizer of all these. He directed all of these experiments. So Rutherford, what he was trying to do, what Rutherford and Hans Geiger, what they were trying to do was they were trying to see how the alpha particle, beam of alpha particles behaved when they hit various metal foils. Okay, so very thin metal foils means very thin pieces, like just like this paper, this tissue paper, very thin pieces of actual foil, right? So if you have seen aluminum foil which is used in your homes, that is the thin metal foil. Okay, so this just like this thin paper. Of course, gold is the most malleable metal, and so very thin foils of gold they were able to produce, and gold was predominantly used in gold foils were thus predominantly used in their experiments. So the idea was they were able to construct a foil of a gold foil which was only one atom thick. Okay, so that was the thing, that was the ideal thing that they wanted to do. Of course, at that time the technology was not so much, so they could not construct, their gold foils was slightly thicker, but that was the idea, to construct a film as thin as possible. And this film was bombarded with a beam of alpha particles. So you would now ask me, what are alpha particles? See, alpha particles, you have seen helium atom. What is the helium atom? Helium atom, at its nucleus, there are 2 neutrons and 2 protons, and there are 2 electrons rotating around this nucleus. See, if I remove these 2 electrons, if I do away with the electrons, what is left in the center, just the nucleus of the helium atom, that is what is an alpha particle. So alpha particle, Ernest Rutherford was already working with alpha particles, and he was the one actually who devised a mechanism of detecting alpha particles. Now see, if I am working with alpha particles, I am doing experiments with them, then definitely I would want to detect those. Where do those particles go after my experiment? That was the entire idea. So he found out that the zinc sulfide, okay, when alpha particle hits zinc sulfide, a plate of zinc sulfide, then it produces a flash. So there is a very faint flash. Those are known as scintillations, okay, flashes. Very faint flash is actually observed at those points. But those are faint, those are not very bright. So what would Geiger and Rutherford do? They would actually go into their laboratory and they would wait for a little while and make it absolutely dark, so that their eyes got used to the darkness. And after a little while only, they were able to actually start their experiments. And the experiments were actually very, very painful. They were actually very, very tiresome. Why was they tiresome? See, this was the fluorescent screen. Of course, we have shown here this entirety of fluorescent screen. We have just covered the gold foil completely with the fluorescent screen, or this was the zinc sulfide screen, like I said. Okay, so this is ZNS, zinc sulfide screen. But they only had a single screen which they rotated all through. Okay, so they would rotate it in different places and then observe the scintillations made by the alpha particles when after they hit this gold foil. Okay, so that was the entire idea of the experiment. Now, behind this zinc sulfide screen was a microscope. So they would observe the scintillations or the flashes only through the microscope. Okay, that's how faint the actual flashes were. So it was very painstaking, very, very difficult experiment. And as we know later, Geiger actually invented the digital Geiger counter, which is the digital equivalent of this detection mechanism, and it could actually count how many alpha particles are hitting its surface in 1 second. Okay, so it could actually count it digitally, and I'm sure because of all this work that he had to do, this was the inspiration for creating something simpler to actually detect the alpha particle, count the alpha particles. So what would then happen is that they would just take this screen at various places around this gold foil and observe the alpha particles reaching at that particular location. So that was it. The experiment itself was very simple. So initially what they did was Rutherford and Geiger, they just thought that let's just put the screen right in front here, like as any experimenter would do. And what they observed was that there was some divergence in the beam of alpha particles, but most of the alpha particles are actually getting here, right? So most of the alpha particles actually reached here, although there was a slight expansion, slight divergence, okay, slight diffraction in that beam, dispersion in that beam. So that's what they were able to observe, which actually was in accordance with the Thomson's model. Thomson's model predicts that the entire atom is homogeneous. So if I were to actually pass a beam of alpha particles through Thomson's model, this is what I would observe, that all the alpha particles, most of them would actually just go straight through, because there are only small electrons present here and there, so there might be small deflections because of those, and that is what they were able to observe. So at first they didn't think that something unusual was actually happening. Then Rutherford had an idea that let us just ask, there is this person Marson, so let's just ask him to observe if there are any alpha particles which are observed behind the gold foil. Okay, so in the sense that which were observed, which had large deflection. Okay, so which were observed behind. This is the front of gold foil, and they were actually observed behind the gold foil, that is towards the source. Are there any alpha particles which are completely reflected back, or are they reflected at large angles? So that is what the Marson was asked to do, and to their surprise, they were actually able to detect alpha particles even behind the gold foil, which means that towards the source of the alpha particle beam, they were able to detect these particles, which could never happen with Thomson's model, because Thomson's model was homogeneous. So all the particles would just go through. Okay, there were only small electrons that could not result in such a deflection, right? See, the alpha particle beam is a beam of heavy particles. They are much heavier than the actual electrons. Okay, first of all, and second is that they have very high velocity. So if what you would observe is that electrons do not have such power to completely deflect the beam, or completely deflect even one particle of the beam of alpha particles. They do not have such power. Okay, they don't have the mass, and of course they cannot do it with the charge itself. Okay, so such a thing was not possible, not explained by our standard Thomson's model. So to get an understanding of this experiment a little bit more, what we are going to do is we are going to just look at this simulation. There is a simulation. We are going to just look at a simulation of how the Rutherford's experiment, what were the observations actually seen in the Rutherford's experiment. So if you open this simulation, this is available at the Colorado University website. So anyone can go there and actually start the simulation. And what we will do is that we will just start the Rutherford experiment. We will start the alpha particle simulation, and then we will just increase its speed so that we are able to observe. So see, notice that this is the Rutherford's model, and in the Rutherford's atomic model, this is the actual model that we know today. And this is the actual thing that they observed. So these individual circles are actually the atoms. So these are the atoms. Okay, these are actually the atoms, the circle ones, and at the center we know that there is a very heavy nucleus. And if we conduct the experiment, then when an alpha particle actually hits the nucleus, then you can see that it completely reflects back. It just comes back. So let's just see. Every once in a while you will just see that an alpha particle is hitting the nucleus and it is completely being reflected back. So this particular animation, you can just try it at your home also, and this is just to explain how the Rutherford's experiment created this new model. Okay, so these were the observations of the Rutherford's experiment. We already saw this. Most of the alpha particles, like we said, actually pass straight through, and this was not a problem. Okay, even Thomson's model, it predicted that this would indeed be the case. So even in Thomson's model, we would see that most of these particles would actually just pass straight through, and this is what they observed. But there were some particles, right? This was the actual problem. This line item is the actual problem. Okay. There were a few particles which scattered at angles greater than 90 degree, and there were very few which reflected back. And how many were there? There were approximately 1 in 10,000 to 20,000 particles which just reflected back. And this was actually causing the cause of concern, because those can never happen in Thomson model. So to ameliorate or to remove this particular problem, Rutherford said that Thomson's model is actually incorrect. What we actually have in an atom, at its very center, there must be a nucleus which is very, very heavy, and all the charge, all the mass of the atom must be concentrated in this very small region. It must be condensed. This nucleus, it must be massive, and it must be very, very small. Okay. And this would explain, if there was a particle, an alpha particle, which hit this nucleus, then we would observe these high deflections, high angle deflections, or complete reflections of the alpha particles. And of course, since most of the alpha particles went straight through, only 1 in 10,000 to 20,000 came back. It means that nucleus must form a very small portion of the entire atom. So there were two things, right? First thing was that this nucleus is there, it is very, very heavy, and it is at the center. The second thing is most of the atom is actually empty, and this would allow us to it would allow most of the alpha particles to go straight through. So these were the two. This is the Thomson's model, and if Thomson's model was correct, then we would observe the alpha particles going through the gold foil diverge slightly. They would diverge slightly because they would, once in a while, they would be deflected by one of the electrons. This and that would happen. So they would diverge slightly. This is what we would have observed in that case. But Rutherford model actually explains what we saw. Okay, so this is not what we observed. We observed this, and because of what we observed, Rutherford proposed a new model, and which was similar to the solar system model, which was earlier there. Before Thomson, solar system model was there. So Rutherford actually went back to that model in some sense. And if we use Rutherford's model, then we can explain these high angle deflections, and sometimes complete reflections of the alpha particles. It is famously, Rutherford at that time, he commented that when we saw the observations from the experiment, then it was like seeing a bullet hit a tissue paper and then come back to you. Okay, so at that time, if Thomson's model was true, then the bullet can never actually come back. Right? So that was the idea. Thomson's model was true, then nothing should have come back. Everything should have just gone through. Okay, so that was the thing. He was so surprised at these results. Now, of course, we know that the Rutherford model is there. He gave us where the nucleus was and what constituted this nucleus. It was at that time they didn't know about the neutrons, so they only focused about the protons, and they said that Rutherford said that all the protons must be there in the nucleus and electrons must be revolving around the nucleus in orbits. And this, of course, was the planetary model. But Sir Rutherford was only concerned. He was only concerned about the nucleus. That was his primary area of research. So he completely ignored the problem with such orbiting electrons. Right? The problem stayed as is, that if the electrons are orbiting around the nucleus, then they would eventually fall, because slowly and gradually they would lose energy due to the classical mechanics. That was the postulate of classical mechanics, and slowly and gradually they will lose energy and then fall down inside the nucleus because of the negative positive attraction. So that problem was not removed by Rutherford, but he was not concerned with it. He was only concerned about the nucleus. So that's what he said. Okay. Now it was up to Niels Bohr to actually came up with the new model which superseded the Rutherford's model and removed that particular problem from the Rutherford's model. He said that electrons cannot orbit anywhere in the atom. Okay, so they revolve around the nucleus, 100%, definitely, surely. They revolve around the nucleus. That is 100% true. They have orbits around the nucleus. But their orbit cannot be anywhere they want. Their orbits are in very specific locations. Okay, so if these specific locations, those are known as stable orbits. In these stable orbits, if the electrons are revolving in these stable orbits, if they are going around in these stable orbits, then these orbits have a special property. And what is the property? That they would not lose any energy. So these stable orbits, they are known as stationary orbits. And these stationary orbits occur at very specific location inside the atom. And if an electron is inside one of these special orbits and it's rotating there, revolving there around the nucleus, then it would not lose energy. Like so classical physics, the problem is actually solved. Okay, and this was the quantum mechanical model of the atom. Okay, so now you would say that I have not really explained why these stable orbits are stable. Okay, why is it that only these orbits can occur and no other orbits can occur? And I've just used a word here, quantum mechanical, and did away with all of these questions. Okay, that's what you would say. That's what we'll see, and most of the places we might do. We will just say that, oh, this is quantum mechanical, and do away with all the questions, because quantum mechanics is not something that we always study. Okay, but we will try to get an understanding of why this happens in a second. Okay, but before we go there, let's just complete this. Okay, the stationary orbits have a special property that the angular momentum of the electron is an integral multiple of Planck's constant. So Planck's constant is just a constant, and integral multiple of Planck's constant means n into s. So Planck's constant is denoted by h. Okay, so the angular momentum of these electrons is equal to nh. Okay, so this is what the special property of this stationary orbit is. Now let's just understand it from a slightly different angle. Okay, let's just understand it from a slightly different angle. See, the quantum mechanical picture was given by Einstein also. And what Einstein said in his with his photoelectric effect was that what was actually said was the energy that I provide to anybody, right? So for example, there is this body, there is this remote control, this thing there. I am pushing it. You will say that I can push it with any force that I want. I can supply it any amount of energy that I want, right? That's what you would say. If I supply it large amount of energy, then it would move with fast velocity, but I can attain any velocity that I want. Whatever real number you can choose, I can give it that velocity. So you will say that the velocity and the energy that I give to this remote control is actually continuous. It can take any sort of energy that I want, any real numbered energy that I want to give it. But if we go to very small scales, very small scales, then we would understand that the energy is actually not continuous. It is discrete, and this is the basic property of the quantum mechanics, that the energy comes in small packets of energy. So I cannot give half packet of energy. I can only give one full packet of energy to someone. Okay, at these large scales, because the energy required is so much, we cannot distinguish how many packets I am giving it just by looking at the velocity of this object. But when I go to small scales, the energy becomes very small. So energy given to an electron to make it rotate in one of these orbits is very small, and that can only be imparted in this fixed quanta or fixed packets of energy. And when I give electron a certain number of such packets of energy, then it can go to the next orbital. I cannot give partial quanta, so I cannot give half a bag of energy, half a packet of energy, and therefore I cannot really attain any orbit. So let's say that in going from this first orbit to second orbit, I really need one quanta or one packet of energy. Then I don't have the ability that's what we have observed, that I don't really have an ability to give half a packet of energies. So therefore, I cannot move this electron between this orbit and this orbit. Either it will be in this orbit, if I give it energy, it will come to this orbit and start revolving there. But I cannot take it in between because I don't have the ability to provide it energy which would take it in the middle. And that's the basic understanding of the Bohr's model, and that is the basic understanding about the quantization of these orbitals, as to why these orbits are quantized, which means they just cannot take any value, but they can take these fixed values which Bohr described in his model. So we have a question here, so let's hear it.
So how was it proved that when we give it a certain amount of energy, and after some time the energy would be released? So when the energy level goes down, the atom will collapse.
See, the thing is that in these stable orbits, the energy is not released. The energy is fixed. And in this stable orbit, the energy is not released. If I excite the electron, okay, so this is the stable configuration of this particular atom. This is the stable configuration. Now, if I excite one of these electrons and move it to the next energy level, then the atom itself has become unstable, because I needed two electrons. I needed two electrons in this lower orbit, lowest orbital, and I moved one of those electrons and I took it to the next higher energy orbit. I gave it energy, I pushed it to the next higher level of energy. Now the atom itself has become unstable. So in that case and that case only, I would see that the electron would try to give energy and go back to the lower orbital, because the lower orbital is empty. There can be one electron there, okay, and we will later on study that the lower orbitals are more stable, so electrons try to go there. So if there is space available in one of those lower orbits, then the electron would jump from the higher orbit and come to the lower orbit. But if there is no space available, then it cannot really jump and impart energy. Okay, but in any case, if the energy is released or given, it has to be given in certain number of packets. It cannot be anything continuous. And this was the basic idea why Bohr's model actually succeeded, because he completely did away with the problem of the stability of electrons in the orbits by saying that these orbits and the energy in these orbits is actually quantized. Okay, so with this we will end this lecture. Of course, as we go along, we will take much more things in greater detail, and we will come up with the numericals based on these questions as well. Okay, thank you.